This is Jack Jackson, and this is a video for calculus. It's going to review some properties of power functions. So a basic power function is just f of x equals x to the n, where, of course, x is our variable, n is a constant power, and I'm also going to include here, if we throw in a constant multiple in the front, a coefficient a, which is also a real constant. So the first thing we want to do here is prove that power functions are continuous where they're defined. Okay, so let's see if we can do that. Well, really, the proof follows very quickly from the results that we had earlier and the laws of limits. So the limit as x approaches c of f of x is a limit of course, f of x is a times x to the n. And our constant multiple rule for limits says we can pull the constant multiple out front of the limit sign, provided this limit exists. And then we have a rule that we proved earlier, at least for natural number powers, which is all we need for power functions, where it says that the limit of something to a power here is the limit and then to the power. And then we can say that this limit of x, of course, is just c, and so that is f of c. So by definition, power functions are continuous where they're defined. Now it did require that this function be defined there. And so there are some types of power functions that are not defined for at certain places. Particularly, we can't have 0 to the 0 power or 0 to negative power. So as long as we don't have those things happening, then we have a continuous function everywhere. If we do have those things happening, then that gives us a discontinuity there. So let's look at some of the graph characteristics for just a basic power function, f of x equals x to the n. So for these basic power functions, remember that a positive number to a positive power is always positive, so that always includes quadrant 1 points, but never any points in quadrant 4. And in particular, 1 to any power is 1, so the point 1, 1 is in common for all these functions. If the power is positive, 0 to the positive power is 0, so 0, 0 is a common point if the power is positive. But if we have a negative or 0 power, they're undefined for x equals 0. To the right of x equals 1, the higher the power is, the higher the graph is. Between 0 and 1, the order is reversed. So the higher powers have lower graphs. So here's several graphs in the first quadrant. They go through 1, 1. All these going through 0, 0 here have positive powers. Here's the power 0 is a horizontal line with a hole in it right here at 0, 1. And if the power is negative, it has a vertical asymptote here. So notice that these ones that are decreasing this way with vertical asymptote here, the x-axis and horizontal vertical of the y-axis, horizontal of the x-axis, these are negative powers, and lower negative powers are down here, and then the higher negative powers here. We get to power 0, it's horizontal, with a hole in it right here. When the power is positive, these functions are increasing in the first quadrant. The bigger the power, the sort of faster it increases eventually. And so, like this is a power less than 1, these that are concave down increasing. And this one that goes through 1, 1 and 2, 2 right here that's straight, that's a straight line. That's just the identity function, y equals x to the first power. And we get powers bigger than 1, they're concave up and increasing here. So summarizing that, when we look at just the first quadrant, if the power is bigger than 1, it goes through 0, 0, and 1, 1, concave up, increasing. Specifically, power 1 is the identity function, y equals x. That's linear, going through 0, 0, 1, 1. If its n is between 0 and 1, it's concave down, like an upside down bowl, this way, and increasing. So all those were increasing. When the power is 0, it's a horizontal line with a hole in it, so it's constant in the first quadrant. If the power is negative, they all look basically the same in the first quadrant. They have asymptotes here, vertical and horizontal of both axes. It does go through 1, 1, but it doesn't go through 0 on x or y axis, either one. So has a limit as we go out here of 0, and the limit as x approaches 0 from the right is positive infinity. So when we summarize, okay, the next thing we want to look at is we're going to summarize what happens in the other quadrants. You have some interesting things going on here. If n is an irrational number or it's a rational number of the form p over q where it's reduced, okay, where the greatest common divisor of the numerator and denominator is 1, it's a reduced fraction, and p is odd and q is even, so odd over even, we're taking an odd power and then an even root, then you only get first quadrant. So there's nothing else besides that. And so there's no symmetry involved there. And there's nothing else besides the first quadrant. Those will be continuous functions because it's all one connected piece in the first quadrant. If the power is p over q, where p is even and q is odd, that's an even over an odd power, that's going to be quadrants 1 and 2, and the part in quadrant 2 is a mirror image of what's in quadrant 1. So it has y-axis symmetry. If it is odd over odd power, okay, so an odd power, an odd root, that's going to take a negative number to a negative number. So that's going to be quadrant 1 and 3, and the part in quadrant 3 is a rotated image 180 degrees about the origin of the first quadrant. So that has origin symmetry. So when you put all this together, here are the basic shapes. I think there's 11 of these basic shapes you come up with. So all of these with n bigger than 1 are increasing concave up in the first quadrant here. And if it is irrational or a power odd over even, okay, then it's quadrant 1 and that's it. So notice that's continuous. If it's a power where it is even over odd, it's quadrant 1 and 2. The second quadrant is a mirror image of the first quadrant. Notice it comes down and up. That's concave up the whole time, but it decreases then increases. So it has a minimum there. Okay, that's all one connected continuous piece. If we have the power is odd over odd, that turns out to be quadrants 1 and 3. And the part in quadrant 3 is a rotated image of quadrant 1. So it's increasing the entire way. So that's a 1-to-1 function. And it's concave down in the third quadrant, concave up in the first quadrant. We have a point of inflection where it changes concavity when x is 0. Of course, n equals 1 is just y equals x. We know what that looks like. Straight line increasing. These are blacked out because that's not a possibility, because that's a specific function. These others are classes of functions, categories. If n equals between 0 and 1, we get concave down but increasing in the first quadrant. And again, if it's an irrational power or odd over even, then it's quadrant 1 only. If it's quadrant 1 and 2, when it's even over odd, and odd over odd is quadrant 1 and 3. So notice your symmetry, mirror reflection, reflective symmetry here when it's even over odd, and odd over odd, rotational symmetry there. So here we have a minimum here we have an inflection point here. But notice all of these are increasing in the first quadrant, and in fact these are all continuous functions. When you have n equals 0, that's x to the 0, that's just the same as y equals 1, but it has a hole in the graph. We looked at this one really early on in these notes. If n is a negative number, they all have are all defined at 0, and the first quadrant looks the same. It's decreasing concave up with these asymptotes, both the vertical and horizontal. Again, if the power is all of these where the power is odd over even or just an irrational power, we only get the first quadrant. So those are all continuous functions. Now these over here are not continuous functions because they have a discontinuity at 0, and they're continuous everywhere in their domain, but the domain's not one connected piece. It skips over x equals 0 for these three that have the blue background. Okay, and you can see what's happening there. Again, y-axis symmetry here, origin symmetry here. So lots of cool things. You can just take a really super simple formula, y equals x to the n, where n's a constant, and by looking at the different constants, we got to talk about all kinds of things like a hole in the graph, vertical asymptote, symmetry, concavity, increasing, minimum, bunch of cool things that we're interested in graphs. Now, if we throw in the coefficient a and say f of x is a times x to the n, what the a does is going to give you a vertical stretch. If the absolute value is greater than 1, that's going to be a vertical stretch or expansion away from the x-axis. If absolute value lays between 0 and 1, that's going to squish it or compress it vertically. That's technically called a vertical strain. And if the x is negative, however, it's going to flip it upside down. So, for example, here, if x is negative, this is going to be upside down, and it's going to approach negative infinity over here in the fourth quadrant. And it'll be a third and fourth quadrant instead of first and second, and so forth. So a negative is going to flip all those pictures upside down.